Hi, everyone. Because of the power outage, the attendance the last couple of days has not been great, and I think some of that might be related to the fact that we did not have power for a good part of Thursday. Since what we are covering right now, I feel is so crucial to what we will be doing for the rest of the semester, I'm concerned that if I do not try to make sure that everyone is on the same page, that the people who were unable to come to class because of potentially something related to the power outage, that would be very unfair to them. So what I'm going to do is I'm going to recap the last 3 lectures. It's going to be very quick, which is okay because in a recording you could always stop and go back if it's too fast. And just hit the highlights of what you should take away from these last 3 lectures. So let's see, Wednesday's lecture, we started talking about energy and the great conservation laws. So if I were to define energy, this actually would be a very challenging thing to do. Even today, we do not really have a solid definition on what fundamentally energy is. We know the properties of energy. We know how energy can be transferred and transformed from one object and transformed into different kinds of energies. But if you really had to think, at a fundamental level what energy is, we still do not really know. You are very familiar with the ideas of energy, the energy of a light bulb, power plants, we were without power, which is power is a transfer of energy. And energy can take many forms. And we'll see that by thinking about energy, this will give us an alternative way of solving problems and determining motion in our systems. Where Newton's laws allowed us to speak very specifically about what's happening at any instant in time. For example, at any instant in time, we could use Newton's laws to get the acceleration at an instantaneous moment in time. Energy will allow us to think or look a little bit more globally, where we will be able to just look at, say, if you have an object that is moving down a ramp, just by knowing the properties of what the ball is doing at the beginning will immediately allow us to say something about what's going on when the ball reaches the bottom of the ramp, without needing to know any of the details of what happened when it gets from its starting point to its ending point. So energy, it is not a replacement of Newton's laws, it is not a correction to Newton's laws, it is just an alternative way of assessing motion in the universe. And for some problems, we will see it proves to be a very effective way and useful way. So back to the definition of energy. And a definition I might give is that it is a quantity of a system that changes when forces make objects in the system move. So a quantity of a system that changes when forces make objects in the system move. And by quantity, we will see that energy is defined to be a scalar quantity, which will be nice. We get to take a little bit of a break from vectors. Energy is a scalar quantity. It has just a magnitude. It does not possess a direction. I cannot talk about the direction of energy. And where we are going with this ultimately is the idea of the conservation of energy. And what the conservation of energy says is that energy can take many forms, it can be transformed into different kinds of energy. So certain kinds of energy can be turned into other kinds of energy. It can be added and removed from a system. But the total energy never changes. So the idea being that as long as you take into account how energy is changing, if it's turning from one kind of energy to the other, how it's being transported between objects. Objects can impart energy to other objects, or it can take energy from other objects through forces. In your system, energy might be injected into the system. Energy might go out of the system. And as long as you take into full account all the different places that energy is and where energy is going, energy is always conserved. The idea of the conservation of energy is that you can take a physics problem and just turn it into essentially an accounting problem, where as long as you're taking into account all the different kinds of energy and all the different places energy is going or coming from, you can understand what the total energy of a system is. Let me sketch out an analogy to what this means. The idea of conservation might be a little abstract for some of you. You hear this a lot in the everyday world. We should talk about conserving energy. But I just told you that energy is always conserved. So what do I mean by that? In physics, what I mean by conservation is that energy can neither be created nor destroyed, but it can move and be transformed from one kind of energy to another, and also can move from the system in and out of the system and between objects in the system. So in the case of, for example, when people say to conserve energy in the real world, what they really mean in that case is you should make sure to not waste your energy. That the energy you have can take certain forms, and some forms of energy are more useful than others. Conserving energy so that you can use it to power your appliances, that is a useful form of energy, versus if you waste the energy, in which case, for example, sometimes energy that becomes wasted just as a result of heat. Friction is really good at wasting energy, because an object is trying to move, say, across a sandy surface or a rough surface. Friction acts on that object, and you experience this every time you rub your hands together. You rub your hands together, friction is acting between your hands, you feel your hands heating up. That is a result of friction turning the energy of the motion of your hands into heat. Now, in those cases, energy was not created nor destroyed, but the energy just took different shapes. So here's an analogy of what I think of when I'm thinking of conservation of energy. So let's imagine that our system is this, but my system is going to be my personal wealth. Now, your personal wealth can take many forms. One example it can take is that you can have cash. If you have $100 in your pocket, that is part of your personal wealth. You have $100 in cash. But that is not the only form that your personal wealth can take. You can have a savings account, for example. And that is an example of how you might transform some of your personal wealth into something else, but it still is part of your personal wealth. If I take my $100 and I put $50 in my savings account, I now only have $50 in my pocket, but I still have overall $100 in personal wealth because I have $50 in cash and then $50 in my savings account. And if I were to then go back and take $25 of that, out of my savings account, I would then have $75 in cash and still have $25 in my savings account. That would be an example where my personal wealth is not changing. It is just taking different shapes and forms. Another example is if you bought property, you bought objects. You use cash to buy objects, and now the amount of cash you have on hand has gone down, but you now also have objects that have wealth to them, and you could get that cash back by selling the property, for example. But there are other ways that your personal wealth can change. In this case, we would say that your personal wealth never changes. It is always conserved. But your personal wealth can change if you, for example, take a vacation. You take a vacation, that costs money to do. As a result of you paying money, you get the experience of a vacation. But a vacation you cannot tangibly hold. It is not part of your personal wealth. So if you spend money on a vacation, the amount of personal wealth, cash, savings, property, that overall decreases. Another way your personal wealth could decrease is if you have bills. You pay bills, that requires money. So when you pay bills, your personal wealth then decreases. Alternatively, your personal wealth can increase. If you have a job, you get a paycheck. That paycheck you can then turn into cash or savings. That increases your personal wealth. So you can see that these are examples where money, in this case, or personal wealth, can come into the system, it can leave the system, or it can be transformed within the system. And as long as you take into account, as long as you know exactly how much money is coming in, how much money is coming out, and what shapes and forms money is taking inside your system of personal wealth, you can understand perfectly how much money you have or what your total wealth is at any given point in time. Now let's make what is then, with this analogy, how does that analogy compare to what we will be doing in physics, where you have your system. In your system, the energy that we talk about, the first kind of energy will be kinetic energy. So this is energy associated with motion. In physics, is all about studying motion. But we will see that there is a savings account of energy, which we will call potential energy. This is a kind of energy where if your kinetic energy gets turned into potential energy, your kinetic energy or the energy of your motion might go down, but you have the potential to get that energy back. Throwing a ball into the air is a good example of this, we will see. As you throw the ball into the air, the ball slows down. You can think of that as gravity is storing away some energy to give back to the ball. And then once the ball starts to fall back down to the ground, gravity then gives that energy back to the ball. And it gains kinetic energy back. So in this case, energy is taking multiple forms, either in motion or being stored in gravity. And if you have only kinetic energy and only potential energies, as long as you keep track of what kinds of energy is in your system, all that energy the total amount of energy will always remain the same. Now, there are ways in which your system, the energy in that system, can change. And again, I'm using words here that I have not defined yet, but again, the point here is that I'm just giving a bigger a broader, bigger picture of what is happening and where we are going. So one way to have energy leave the system is through what we will call non-conservative forces. So friction is a great example of a non-conservative force. Friction likes to turn kinetic energy into thermal energy or heat, again, which is why your hands heat up when you rub them together. And that is energy that you cannot get back. If the system is my two hands, I rub my hands together, my hands slow down as a result of the rubbing. My hands also, though, heat up, and that energy cannot be regained. I don't know if you can hear that laughter, but apparently the faculty are having a party outside my office. How else can it change? So another way that energy can be changed is that the system changes itself. If the system is, say, a solar system, a star and a couple planets, and one of the planets gets thrown out of the system, that planet is going to take some energy with it. And so if things enter and leave the system, that can change the energy of the system. And then energy can be injected into the system by something that we will call external work. And again, don't worry too much about these terms. They will be defined. So this could be an example of if my system were a box and my system is just the box, I could add energy into the system if I then start pushing on the box. I am not part of the system, but I am doing work that will allow the box to accelerate and speed up, and it will gain kinetic energy as a result. So you can do work on the system to put energy into the system. Energy can also leave the system through non-conservative forces like friction, or the system itself could possibly change. So this is kind of bigger picture idea of where we are going with the idea of conservation of energy. Again, as long as you take into account how energy is changing, what shapes the energy has, and then how energy is entering and leaving the system, you can always know at any given point in time the total energy of the system, which we will use to relate to the motion of objects in the system. Now, before we get to energy, though, we have to do a little bit more with vectors. So I need to teach you how to multiply two vectors together. That is going to be very useful when we talk about energy and how energy is transported between objects in a system. So this is, we'll call this ultimately relates to the dot product and vectors. So let me motivate this a little bit. In the past, we have had problems like where we have some coordinate system, x and y, and we have some vector a. And we were curious to know, how much does this vector point in the horizontal direction? We might call that a sub x. And then how much does this vector point in the vertical direction? We might call that a sub y. And recall, just by trig functions, that these guys were given by an application of SOHCAHTOA, assuming that the angle that it makes with the axis is theta. And sometimes our axes were not perfectly horizontal and vertical like in that case. For example, when we had a box moving down an incline, you might have some vector g that was pointing straight down, but there was a direction that was I could call this along the ramp if it was an incline, and then this might have been perpendicular to ramp, so into or out of the ramp. And in that case, we were also curious to know if I knew this angle, I could break this vector into a part that moves along the ramp and break this vector into a part that is perpendicular to the direction of the ramp, for example. Given the way I wrote this, if that is the angle, then this would be, for example, g cosine theta, and this would be g sine theta. Now suppose I have two different vectors. I'll call this v, and I have another vector that I will call w. So two arbitrary vectors that are pointing in two different directions. We might still be interested in asking the same question. You can see that these guys are almost parallel to one another. So there is a part of v that points in the same direction as w, and there is a part of v that points perpendicular to w. So I might call this v perpendicular, and then I might call this v parallel. The part of the vector v that is parallel to w, and the part of the vector v that is perpendicular to w. For example, an example I think I gave in class is, if you have a river that you're trying to cross and you're moving, in this direction along the river, you might, and I asked you, how long does it take you to cross the river? Since you are not moving directly across the river in this case, it is useful then for you to know, for this vector, what part of that vector points in the direction that allows you to cross the river, and then there's a part of the vector that points in the direction, moving downriver. So I could ask a question like, by the time you make it across the river, how far downstream have you rowed, for example? Just one example of where this might pop up. Now in this case, if we happened to know this angle, if we knew the angle between these two vectors, then you may notice that this is no different than what we have written before. And if I knew the angle between the two vectors, and I could find the component of v that points in the same direction as w, just as the magnitude of the vector v times cosine of that angle, if we knew theta. And the dot product, this way of multiplying two vectors together, we'll see is one way of determining that angle. So there are two ways you can define the dot product. And it turns out, obviously, that they will be equivalent, and we'll show that they're equivalent. So suppose you have two vectors, A and another vector B. And I'll do this in 3 dimensions, but this is true whether it's 2 dimensions, 3 dimensions, 12 dimensions. If A is some vector that has an x component, a y component, and a z component, and B is also a vector that has an x component, a y component, and a z component, then I can define the dot product, which I'll write as A dot B, as a scalar that is equal to the product of the x components added to the product of the y components added to the product of the z components. This is one way that you can define the dot product, where you take the, for each coordinate there is, depending on how many dimensions there are, you multiply them together, and then you add up all the products. So to give an example, I'll give a 2D example. If A equals 1, 2, and B equals 3, 4, then A dot B is 1 times 3 plus 2 times 4, or 3 plus 8, or 11. Notice the answer is a scalar. Two vectors come in and only a number comes out. The dot product returns a scalar. So sometimes you'll see this defined as called not the dot product, but the scalar product. You multiply two vectors together and you get just a number out. You don't have a direction. There's no direction associated with 11 right here. Now you are probably wondering, how on earth is this useful? Seems like I just arbitrarily made it up. But notice, one useful relation with the dot product is if I take the dot product of a vector with itself, then you can convince yourself that this is the sum of the squares of the components of the vector. This is the same thing as the square of the magnitude of the vector. This actually, in some cases, is how people define the magnitude of the vector. You take a vector, you dot it with itself, that is the square of the magnitude of the vector. Or similarly, you could say that the magnitude of the vector is the square root of the dot product. The dot product also, the dot product is nice because it obeys a lot of the same rules that regular multiplication obeys. So for example, a vector, if I have vectors b and c, we know how to add vectors together. That was chapter 3. That gives me a new vector. And then if I wanted to take the dot product of that new vector with a, you can easily convince yourself that that is the same thing as if you took the dot product of the two original vectors with a and added it together. So we would say that the dot product distributes. The dot product also commutes. Like regular multiplication, it does not matter the order of things. And now this will be useful because we can now derive a different way to define the dot product. And with this, we'll see that the dot product ties in it the angle between the two vectors. If we know the dot product, we can figure out the angle between the two vectors. So the way we will do this is I will start by, and I will draw some vector A, some vector B, and then we learned that I could draw this vector here, which is A minus B. A minus B, again, remember, points to A from B. That's how I always remember it. In this case, they make some angle theta with one another, the original two vectors, and the hope is that we can do something to figure out what that angle is. Now notice in this case, I have drawn a triangle using the three vectors. And now it's not a right triangle, so SOHCAHTOA does not apply, but we can use the law of cosines in order to relate the lengths of the three sides of the triangle. So the law of cosines, all that says is the length of one side of the triangle plus the length of the other side of the triangle. Sorry, the sum of the squares of the length of the triangle. Pythagorean theorem says that this is equal to the square of the hypotenuse. The law of cosines actually is a generalization of the Pythagorean theorem. So it has this additional term in it. Minus 2 times the magnitude of one side, the magnitude of the other side, times the cosine of the angle between the two. That'll be useful. And then that is equal to the square of the hypotenuse, which in this case is a minus b, the magnitude of whatever that vector is squared. Again, notice that if this were a 90-degree angle where theta was 90, the cosine of 90 degrees is 0. This just turns back into the Pythagorean theorem. Now, what will be useful here is using one of the properties of the dot product that we just talked about, which is this guy right here, that the dot product is equal to the square of the magnitude. But here we're going to go in the opposite direction. So on the right-hand side here, I have the square of the magnitude. That then is the same thing as a minus b dotted with itself, a minus b. But we also just said that the dot product distributes. So this is the same thing as a dot a plus b dot b. Here, use the FOIL method or whatever it's called these days, to a dot b. Now this is nice because a dotted with itself, that is just the magnitude of a squared. B dotted with itself, that is the magnitude of b squared. And then we got what's left over, 2a dot b. Now let me just recopy this top line down below. So this says that the magnitude of a squared plus the magnitude of b squared minus 2 the magnitude of a, the magnitude of b, cosine of theta equals the magnitude of a plus the square of the magnitude of b squared minus 2ab. Now notice there are some things that are on both sides. Both sides has a squared, both sides has a b squared. Now all that's left is one term on both sides. This is minus 2, the magnitude of a, magnitude of b, cosine of theta. That's equal to minus 2 a dot b. I could divide by negative 2 to get the negative 2's to go away. And at the end of the day, notice I have a magnitude of a times the magnitude of b times the cosine of theta equals a dot b. So using the law of cosines, we actually have a relationship now between the angle between the two vectors a and b and the dot product. If you take the dot product, all this is saying is that the dot product is equal to the magnitude of the two vectors, or the product of their magnitudes, times the cosine of the angle between them. So if you know the dot product and you know the magnitudes of the two vectors, then you know everything. You can then solve for cosine of that angle, or solve for the angle itself. You know, for example, let's go back up here to our 2D example. We already solved for the dot product. It is easy enough to show that the magnitude of A is square root of 5. The magnitude of B is, let's see, 9 plus 16 all in the square root. That is the square root of 25, which is itself just 5. So what this says is that the dot product, 11, equals 5 square root of 5 times cosine of theta, which says that theta is about 10 point, I think it was like 10.5 degrees or so. 10.3 degrees, my notes say. So again, the dot product will be useful because it is a way for us to find the angle between the two vectors. All right, that's it for the first of these 3 makeup lectures.